Right now, you're drifting through the largest empty region ever discovered, a bubble 2 billion light-years wide, where matter itself is 20% missing. Scientists just confirmed it using echoes from the Big Bang, and the proof is undeniable, 100 million times more likely than coincidence. This void surrounds Earth, the Milky Way, everything you've ever known. It's been hiding in plain sight, warping our measurements, breaking our models of reality. And it means the universe is stranger than we imagined. If you're enjoying this journey into the unknown, hit that like button. Let's dive in. Scientists measure how fast the universe expands by looking at distant galaxies racing away from us. They calculate this rate, called the Hubble constant, in two completely different ways. The first method examines ancient light from when the universe was only 380,000 years old. This cosmic microwave background reveals an expansion rate of 67 kilometers per second per megaparsec. The second method studies nearby stars and exploding supernovae. These observations give 73 kilometers per second per megaparsec. 6 units of difference. That might sound small, but it's catastrophic. Both measurements have been refined for years. The precision keeps improving. The contradiction refuses to disappear. Nobel laureate Adam Rees said it plainly. Our measurements keep getting more precise, and the tension doesn't go away. This isn't experimental error. When the James Webb Space Telescope checked the work, it confirmed the discrepancy. Something fundamental about our understanding is wrong. Either the early universe behaved differently than our models predict, or we're measuring the local universe incorrectly, or perhaps something even stranger is happening. Scientists call this the Hubble tension, but that's too gentle a term. This is a crisis in cosmology. Our best theory, lambda cold dark matter, has predicted countless phenomena correctly. It explains galaxy formation, element abundances, the cosmic microwave background's temperature variations. Yet it cannot reconcile these two expansion rates. The tension has passed the 5 sigma threshold, meaning there's only a 1 in a million chance this is random variation. For a decade, researchers hoped the problem would resolve itself. Better instruments would reveal a mistake. More data would bring the numbers together. Instead, the opposite happened. Every new measurement deepened the mystery. What could cause the universe to expand at 2 different rates? The answer, it turns out, might be hiding in the space around us. Before galaxies, before stars, before atoms themselves, the universe was a screaming ocean of sound. In the first 400,000 years after creation, space contained only plasma. Charged particles and photons locked together in a hot, dense fluid. Pressure and gravity fought each other in this cosmic soup. Imagine dropping stones into a pond, ripples spread outward in perfect circles. Now imagine billions of stones dropped simultaneously. The early universe was like that, except the ripples were sound waves propagating through plasma at over half the speed of light. These weren't sounds anyone could hear. They were pressure waves on a scale that defies human comprehension. Regions slightly denser than average would collapse under their own gravity, but the intense radiation pressure would push back. This created oscillations, vast bubbles of compressed and rarefied plasma expanding outward. The waves carried normal matter with them, while dark matter, interacting only through gravity, stayed behind at each wave's origin. Then, 380,000 years in, the universe cooled enough for atoms to form. Electrons and protons combined into neutral hydrogen. Suddenly, photons could travel freely. The pressure supporting the sound waves vanished instantly. The waves froze exactly where they were, like ripples on a pond turned to ice mid-motion. Those frozen ripples still exist today. They've expanded with the universe itself, stretched across billions of light years. We call them baryon acoustic oscillations. They left permanent imprints on where matter clusters. Galaxies are slightly more likely to form at specific distances from each other. distances determined by how far those ancient sound waves traveled before freezing. That distance was about 450,000 light-years when the waves stopped. Today, after 13.8 billion years of cosmic expansion, that same distance has stretched to 500 million light-years. Astronomers can measure this distance by counting galaxy pairs. There's a small but measurable excess of galaxies separated by exactly 500 million light-years compared to slightly smaller or larger distances. This pattern appears everywhere we look across the cosmos. But here's what makes this incredible: that 500 million light-year ruler never changes. It's determined entirely by the physics of the early universe. How fast sound traveled through the primordial plasma, how long before atoms formed, the temperature and density of matter back then. Because we know these conditions precisely from studying the cosmic microwave background, we know exactly how long our ruler should be. And because this ruler appears in the galaxy distribution at different cosmic ages, we can measure how the universe has expanded over time. But what if that ruler looks different depending on where you're standing? What if living in a particular region of space distorts the pattern? That's exactly what scientists discovered. Count the galaxies in every direction. Look as far as telescopes can see. Something's wrong with the numbers. Within 1 billion light-years of Earth, there are noticeably fewer galaxies than there should be. The light reaching us from distant regions, those 1.5 billion light-years away, is 50% brighter per unit volume than light from our immediate neighborhood. Imagine living in a suburban house. When you look at the night sky, most of the glow comes from distant cities rather than nearby homes. That's our cosmic situation. We're in the suburbs. The cities are far away. This pattern first emerged in 2013 when astronomers Ryan Keenan, Amy Barger, and Lennox Cowie analyzed 35,000 galaxies from multiple surveys. They noticed something disturbing. Matter density drops as you approach our location. It's not a small effect. Measurements suggest the region around us is 15 to 50% less dense than the cosmic average. They named it the KBC void, after their initials. Some scientists prefer calling it the local hole, which sounds less technical but more unsettling. This underdensity is enormous. It spans roughly 2 billion light-years across. That's 600 megaparsecs in astronomical units. For comparison, our entire local group of galaxies, including the Milky Way and Andromeda, measures only 10 million light-years across. The void is 200 times wider. But voids aren't completely empty. They're regions where galaxies are scarcer. Instead of finding hundreds of galaxies in a given volume, you might find only 50. The matter is still there, just spread thinner. Our void contains the Milky Way, the local group, and much of the Laniakea supercluster, which includes over 100,000 galaxies. Yet, compared to the universe's average density, we're in a relative desert. The Milky Way sits not at the void's edge, but near its center, within a few 100 million light-years of the middle. This position is crucial. If we were at the edge, we'd see asymmetric galaxy distributions. Instead, the underdensity surrounds us fairly uniformly in most directions. Multiple surveys across different wavelengths confirm this structure. Optical telescopes, infrared observations, X-ray detectors, radio telescopes all see the same pattern. Fewer galaxies nearby. More galaxies far away. The galaxy distribution doesn't lie. But how could such an enormous, underdense region exist? And what does it mean for our observations of the universe? Imagine removing 1/5 of everything around you. 1 out of every 5 galaxies gone. 1/5 of the dark matter vanished. That's what living in the KBC void means. The difference sounds modest, 20% below average. But at cosmic scales, this represents a staggering amount of missing mass. To understand the implications, consider what holds the universe together. Gravity. Every particle of matter attracts every other particle. Where matter clusters densely, gravity grows stronger. These regions pull additional material toward them, becoming even denser. Where matter is sparse, gravity weakens. Material drifts away towards stronger gravitational fields. Voids grow emptier over time. This process has been happening for nearly 14 billion years. The KBC void's 20% density deficit translates to specific, measurable effects. First, the gravitational potential. Dense regions create gravitational wells, like valleys. Underdense regions create gravitational hills, like mountains. Objects naturally roll downhill. In space, this means galaxies flow from low-density to high-density regions. The void acts like a giant mountain, pushing everything away from its center. Second, the expansion rate. Space itself expands everywhere, but local gravitational effects can make regions appear to expand faster or slower. Inside a void, there's less matter to gravitationally slow the expansion. The reduced density allows space to expand more freely. This creates an apparent acceleration in the local expansion rate. For galaxies inside the void, those density effects are real. When we measure how fast nearby galaxies recede from us, we're measuring expansion within an underdense bubble. Those measurements don't represent the universe's average expansion rate. They represent expansion within a special location. Think of it this way. If you measured temperature in Death Valley, you'd get readings consistently higher than Earth's average. That doesn't mean the planet is hotter than we think. It means you're standing in an unusually hot location. We might be doing the cosmic equivalent with expansion measurements. But here's the controversy. The lambda-cold dark matter model, our standard cosmology theory, predicts the universe should be remarkably uniform at large scales. Small variations exist, of course. Galaxies cluster into groups. Groups form superclusters. But average the density over hundreds of millions of light years, and it should be nearly the same everywhere. A void 2 billion light-years wide with 20% lower density shouldn't exist, not according to standard cosmology. The probability of such a structure forming randomly is incredibly low. Some calculations suggest odds of 1 in a billion, yet the observations clearly show we're in an underdense region. Multiple independent measurements confirm it. So either we're incredibly unlucky to live in such a rare location, or our cosmological model is incomplete. There's a third possibility. Maybe what seems rare is actually common, and our models underestimate how clumpy the universe truly is. Voids don't stay static, they evolve, and evolution means emptying out. Here's how it works. The void has lower density than surrounding regions. Those surrounding regions have stronger gravity. Their gravitational pull reaches into the void, tugging at everything inside. Galaxies near the void's edge feel the strongest effects. They accelerate toward the denser exterior. As they leave, the void becomes slightly emptier. The gravitational imbalance grows stronger. More material flows outward. This creates a runaway effect. The void expands and deepens over cosmic time. Scientists call this the void evacuation process. It's been happening since the early universe. Every billion years, more matter drifts from underdense regions toward overdense structures. The flow is measurably fast. Studies show bulk flows of galaxies moving at speeds exceeding 400 kilometers per second over distances of 300 million light-years. These aren't random motions. They're coherent streams, like rivers of galaxies flowing downhill in the cosmic gravitational landscape. The Milky Way itself is caught in this current. Our galaxy rushes away from the void center at nearly 1 million miles per hour. That's 600,000 miles per hour, or roughly 250 kilometers per second, directed outward from the local void center. We're escaping. This outward flow has profound implications for measuring expansion. When we observe a galaxy and measure its redshift, we're seeing two effects combined. First, cosmic expansion itself stretches space between us and that galaxy. Second, the galaxy's motion through space adds additional redshift or subtracts it, depending on direction. Inside a void, most galaxies are moving outward. That means galaxies in most directions have extra redshift added to the cosmic expansion signal. Their total redshift is slightly higher than cosmic expansion alone would produce. When astronomers measure the Hubble constant using nearby galaxies, they're measuring redshifts influenced by void evacuation. The expansion rate appears faster than it truly is. Indranil Banik from the University of St Andrews has calculated this effect precisely. His models show the KBC void could inflate the local Hubble constant measurement by about 11%. That's remarkably close to the observed discrepancy between local and cosmic microwave background measurements. The math is straightforward. If the true expansion rate is 67 km per second per megaparsec and void effects add 11%, you get roughly 74. That matches the local measurements almost exactly, but this explanation only works if we're near the void center. If Earth were at the void's edge, the effects would be asymmetric. We'd see some directions with enhanced expansion and others with normal expansion. Instead, measurements show fairly uniform enhancement in all directions. That places us within a few 100 million light-years of the center. What are the odds of that? Living in a rare giant void is already improbable. Living near its center seems even more suspicious. Unless voids are more common than we think, or there's something special about central locations that makes them more likely to host observers. This anthropic argument makes some scientists uncomfortable, but the data doesn't care about our comfort. You're standing on a moving sidewalk at an airport. People walking toward you seem to approach faster than their actual walking speed. The sidewalk adds its velocity to theirs. Measuring cosmic expansion from inside a void is similar. The void's dynamics add velocity to what we observe. Every measurement tells us something about reality, but interpreting measurements requires understanding context. When Henrietta Swan-Leavitt discovered that Cepheid variable stars' brightness related to their pulsation period, she handed astronomers a cosmic ruler. When Edwin Hubble used that ruler to measure galaxy distances, he discovered the universe expands. When Saul Perlmutter, Adam Rees, and Brian Schmidt used exploding white dwarfs to measure expansion more precisely, they discovered dark energy accelerating that expansion. Each breakthrough assumed they were measuring universal properties. But what if some measurements are local? Inside the KBC void, space does expand. The expansion is real, but it's not representative of the entire universe. It's like measuring rainfall in a desert and concluding Earth is dry, or measuring temperature in Antarctica and concluding the planet is frozen. Local conditions matter. Here's what happens. Light from a distant galaxy travels to us. As it travels, space expands, stretching the light's wavelength. This is redshift. The amount of stretching tells us how much space expanded during the light's journey. More expansion means more redshift. By comparing redshift to distance, we calculate the expansion rate. But inside a void, there's a complication. The galaxy isn't just receding due to expansion. It's also moving through space, evacuating the void, flowing toward denser regions. That motion adds to the redshift. Separating these two effects is nearly impossible with current techniques. Astronomers assume all redshift comes from expansion. They plug the measurements into their equations. They calculate the Hubble constant. They get 73 instead of 67. The difference seems mysterious. It's not. It's void dynamics masquerading as faster expansion. Indranil Banik explains this using gravitational potential. Imagine the universe as a landscape. Dense regions are valleys. Voids are hills. Galaxies roll from hills toward valleys. Their motion isn't expansion, it's falling. But redshift can't distinguish falling from expanding. Both stretch light the same way. The only way to detect this effect is statistical. If you measure enough galaxies in enough directions, patterns emerge. Void evacuation creates systematic biases. All nearby measurements become slightly inflated. The inflation disappears at large distances, beyond the void's edge. This is exactly what observations show. The Hubble tension exists at low redshifts. where measurements sample our local region. At high redshifts, where measurements sample distant universe, the tension vanishes. The cosmic microwave background comes from everywhere simultaneously. It averages over the entire observable universe. CMB measurements give the true average expansion rate. Local measurements give expansion rate inside our void. Both are correct. They're just measuring different things. But accepting this explanation requires accepting something uncomfortable. We live in a special location, not special in any profound sense, just statistically unusual. A place where measurements systematically differ from cosmic averages. That makes cosmology harder. We can't simply assume our backyard represents the universe. We must account for local peculiarities when interpreting data. Some scientists resist this conclusion. They prefer explanations involving new physics, early dark energy, modifications to gravity, time-varying dark energy equation of state. Those explanations are possible, but they're also more complicated. They require inventing new phenomena. The void explanation uses only known physics, gravity, density variations, motion through space, all standard, all well understood. Occam's razor suggests the simpler explanation deserves serious consideration. Science deals in probabilities. When evidence overwhelmingly favors one explanation over alternatives, we pay attention. The KBC void hypothesis just crossed that threshold. 20 years of data, hundreds of measurements, baryon acoustic oscillations detected across vast stretches of space and time, all pointing to the same conclusion. We live in an underdense bubble. The statistical analysis is decisive. Researchers compared two models. First, a model where the universe is uniform, matching standard lambda cold dark matter cosmology, calibrated from Planck satellite observations of the cosmic microwave background. Second, a model including a local void with properties matching the KBC void. Then they asked, which model better explains the observed distribution of baryon acoustic oscillations? The answer wasn't close. The void model is approximately 100 million times more likely than the void-free model. 100 million. That's not a typo. When scientists express this in standard notation, they write 10 to the 8th power. In everyday terms, it means the evidence is overwhelming. For context, particle physicists require 5 sigma significance to claim a discovery. 5 sigma means odds of about 1 in 3.5 million against random chance. The void evidence exceeds that standard by orders of magnitude. This doesn't come from one measurement. It comes from synthesizing decades of observations. Galaxy redshift surveys mapping 3-dimensional structure, measurements of how galaxies cluster at different cosmic epochs, the angular scale of baryon acoustic oscillations at various distances, the peculiar velocities of galaxies indicating bulk flows. Each dataset independently suggests underdensity in our local region. Combined, they become irrefutable. But here's what makes this particularly compelling. The analysis didn't assume a void exists and then look for supporting evidence. That would be confirmation bias. Instead, researchers took all available BAO measurements from multiple surveys over 20 years. They fed this data into models. The models themselves determined whether including a void improved the fit. The improvement was dramatic. Without a void, the models struggled to match observations. Galaxy distributions didn't align with predictions. The cosmic distance ladder showed systematic discrepancies. Expansion measurements varied by location, in ways standard cosmology couldn't explain. With a void, everything clicked into place. The model accurately predicted galaxy clustering patterns. It explained the Hubble tension without invoking new physics. It matched bulk flow measurements, showing matter streaming toward the void's edges. Of course, statistical likelihood isn't certainty. Science never deals in absolute proof. There's always room for alternative explanations. Maybe multiple unrelated systematic errors conspired to create the appearance of a void. Maybe coincidence stacked upon coincidence produced the pattern. Maybe dark matter behaves differently than we think, or dark energy varies with location, or quantum effects operate at cosmic scales. All these possibilities exist, but they're far less probable than the straightforward explanation. We live in a void. The evidence is now strong enough that ignoring it requires rejecting standard statistical inference. Some researchers are doing exactly that. They point out that lambda-cold dark matter predicts voids this large should be incredibly rare. Finding ourselves in one seems too coincidental. This is sometimes called the fine-tuning problem. But rarity isn't impossibility. Rare events happen. Someone wins the lottery despite astronomical odds. Rare genetic mutations occur. Planets form in unusual orbits. We might simply be the observers who happen to live in an unusual location. After all, observers can only exist where conditions permit observation. If voids somehow favor galaxy formation or habitability, intelligent observers would preferentially emerge there. This anthropic reasoning makes some scientists uncomfortable, but it's not unscientific. For a decade, the Hubble tension has been cosmology's most embarrassing problem. 2 methods, 2 answers, 9 kilometers per second per megaparsec of difference. Careers spent trying to find the error. Precision instruments built to resolve the discrepancy. Theoretical physicists proposing exotic solutions. Early dark energy, varying fundamental constants, modified gravity at cosmic scales, sterile neutrinos, quantum vacuum fluctuations, dark radiation, interacting dark energy, decaying dark matter. Each proposal more elaborate than the last, all because 2 measurements disagreed, and all possibly unnecessary. The void provides an elegant solution that requires no new physics. Consider what each method actually measures. The cosmic microwave background method looks at ancient light from when the universe was 380,000 years old. This light comes from every direction simultaneously, sampling the entire observable universe. The temperature fluctuations in this light encode information about cosmic density, composition, and expansion history. Cosmologists take this data. They plug it into lambda-cold dark matter equations. They extrapolate forward 13.8 billion years. The model predicts today's expansion rate should be 67.4 kilometers per second per megaparsec. This is a global average. It represents the universe as a whole. The local method uses completely different physics. It observes pulsating Cepheid variable stars in nearby galaxies to establish distances. Then it measures type Ia supernovae in those same galaxies to calibrate absolute brightnesses. Then it observes more distant supernovae and uses their apparent brightness to calculate distance. Combined with redshift measurements showing how fast these galaxies recede, distance and velocity together yield the Hubble constant. This method gives 73.04 kilometers per second per megaparsec. But there's a crucial detail. This method only samples nearby space. Cepheid variables are only visible out to about 100 million light-years. Type Ia supernovae used for calibration extend perhaps 2 to 3 billion light-years. That distance range sits entirely within the KBC void. The local method measures expansion inside the void. The cosmic microwave background method measures expansion everywhere averaged together. These are different quantities. Imagine measuring the average human height. One scientist measures everyone in the Netherlands, where people are tallest. Another scientist analyzes global census data. The first gets 183 centimeters. The second gets 171 centimeters. Both measurements are correct. They're measuring different populations. This is essentially the Hubble tension, not a contradiction, not a crisis, just local versus global measurements. The void explains why local measurements run high. Galaxies evacuating the void have enhanced redshifts. Less matter means slightly faster expansion. The gravitational gradient causes systematic bias in one direction. Banach's calculations show the effect magnitude matches observations nearly perfectly. An 11% inflation of the Hubble constant brings 67 up to 74, right in line with local measurements. Some details still need work. The void's exact size and density profile require better mapping. The Milky Way's position relative to the void's center needs precision measurement. Alternative explanations need rigorous comparison. But the basic mechanism is clear and testable. If the void explanation is correct, we can make predictions. Measurements beyond 3 billion light-years should show lower Hubble constant values, approaching 67. The Hubble tension should disappear at large distances. Observations should show asymmetry in certain directions where void structure isn't perfectly spherical. Bulk flows should align with void evacuation patterns. These predictions can be tested with next-generation surveys. The James Webb Space Telescope can observe Cepheids at greater distances. The Vera Rubin Observatory will catalog billions of galaxies, mapping structure in unprecedented detail. The Euclid mission will measure baryon acoustic oscillations across cosmic history. Within a decade, the data will either confirm or falsify the void hypothesis. If confirmed, the Hubble tension ends, not with exotic physics, not with revolutionary discoveries, just with the realization that location matters, that measuring the universe from inside a void skews results, that we need to account for local structure when interpreting observations. It's humbling. We're not at a special location. We're at a statistically unusual one. That makes cosmology harder, but at least it doesn't require rewriting physics. You can't see a void directly. It's defined by absence. No bright markers highlight empty regions. Instead, astronomers count what's there and notice what's missing. The techniques are subtle. They require surveying millions of galaxies across billions of light years. They demand precise measurements of position, distance, and velocity. They involve statistical analysis on enormous datasets, but they work. The first method counts galaxy numbers. Survey a large volume of space. Divide it into equal-sized cubic regions. Count how many galaxies appear in each cube. Most cubes have similar numbers. Some have slightly more, forming galaxy clusters and superclusters. Some have slightly fewer, but occasionally you find cubes with far fewer galaxies than average. String together enough underdense cubes and you've found a void. This method revealed the first voids in 1978. The cosmic web structure emerged from galaxy surveys. Dense filaments threading through space, clusters where filaments intersect, voids occupying the space between filaments, like bubbles in foam. The KBC void appeared in surveys starting around 2013. Multiple projects contributed data: the 2-degree Field Galaxy Redshift Survey, the Sloan Digital Sky Survey, the 2-micron All-Sky Survey. Each catalogued thousands of galaxies, measuring their positions and redshifts. Combined, these surveys showed the same pattern: galaxy density drops near the Milky Way. The second method tracks galaxy motions. Every galaxy has 2 velocity components. First, recession velocity from cosmic expansion, which is proportional to distance. Second, peculiar velocity from gravitational influences, typically a few hundred kilometers per second. By measuring total velocity and subtracting expected expansion velocity, astronomers isolate peculiar velocity. These peculiar velocities reveal gravitational structure. Galaxies flow from underdense regions toward overdense regions. Large-scale flow patterns, called bulk flows, indicate massive structures pulling on huge volumes of space. The Cosmic Flows 4 catalog tracks these motions for tens of thousands of galaxies. The data shows systematic flows consistent with void evacuation. Galaxies near the void's edges move outward faster than expansion alone explains. Those at the center show weaker outward motion. The pattern matches predictions for a void roughly 1 billion light-years in radius. The third method uses baryon acoustic oscillations. These frozen sound waves from the early universe create a preferred distance scale in galaxy clustering. By measuring how this scale appears at different distances and different cosmic epochs, astronomers map expansion history. But here's the key insight. A local void distorts the baryon acoustic oscillation scale. The distortion is small but measurable. Void dynamics add redshift, making galaxies appear slightly more distant than they are. This shifts the apparent BAO scale in predictable ways. 20 years of BAO measurements now exist. Multiple surveys at different wavelengths, optical observations from ground-based telescopes, infrared data from space missions. Each dataset independently shows distortions consistent with a local underdensity. The fourth method examines the integrated Sachs-Wolf effect. Photons from the cosmic microwave background gain or lose energy crossing gravitational potentials. When a photon enters a dense region, it blue shifts, climbing out of the gravitational well. When it enters a void, it red shifts, climbing the gravitational hill. In a static universe, these effects cancel. Photons gain energy entering and lose it leaving, ending with their original energy. But the universe expands. Gravitational potentials change while photons cross them. Dense regions become denser, voids become emptier. This leaves a net energy change, imprinting patterns on the cosmic microwave background. Large voids create cold spots in the CMB. The local void should produce exactly such a cold spot in a specific direction. Observations hint at this signature but aren't yet conclusive. Finally, there's gravitational lensing. Mass bends spacetime. Light following curved spacetime takes longer to reach us. By measuring time delays from multiple images of the same distant quasar, astronomers map mass distribution. Voids, having less mass, create weaker lensing. They also create specific patterns in how background galaxies appear distorted. These patterns are subtle. Detecting them requires surveying thousands of square degrees of sky at high resolution. Future missions like Euclid and the Vera Rubin Observatory will provide this data. Together, these methods paint a consistent picture. The local universe is underdense. The underdensity extends roughly 1 billion light-years in radius. It affects galaxy motions, clustering patterns, and cosmic microwave background fluctuations. It's not a measurement error. It's not an artifact of one technique. It's a physical structure confirmed by multiple independent observations. Light from the beginning still surrounds us. 13.8 billion years ago, the universe became transparent. Electrons and protons combined into neutral hydrogen atoms. Photons, previously trapped by constant scattering, suddenly streamed freely through space. They've been traveling ever since. We detect them as the cosmic microwave background. The most perfect blackbody spectrum ever measured. Temperature of 2.725 Kelvin, uniform in all directions to 1 part in 100,000. But those tiny variations matter enormously. Slightly hotter spots correspond to slightly denser regions in the early universe. Slightly cooler spots mark underdense regions. Gravity amplified these variations over billions of years. Dense spots became galaxy clusters. Underdense spots became voids. The cosmic microwave background encodes the initial conditions. The European Space Agency's Planck satellite mapped this radiation with extraordinary precision from 2009 to 2013. The data revealed the universe's composition: 68% dark energy, 27% dark matter, 5% normal matter. These numbers aren't guesses. They're measured from the pattern of hot and cold spots, the way temperature fluctuations correlate at different angular scales. Most importantly, the cosmic microwave background determines cosmological parameters, how much curvature space has, how fast the universe expanded early on, how matter and radiation densities evolved. Plug these parameters into lambda cold dark matter equations, and you can predict the current expansion rate. The Planck team calculated 67.4 kilometers per second per megaparsec. Other cosmic microwave background missions agree. NASA's Wilkinson Microwave Anisotropy Probe gave similar numbers. The Atacama Cosmology Telescope confirmed them. The South Pole Telescope provided independent verification. All these measurements come from the entire observable universe. The cosmic microwave background photons we detect left matter at redshift 1089. They traveled from every direction simultaneously. They sample the whole cosmos, averaged together. This is crucial. The cosmic microwave background can't tell us about local structure. It shows only the global average. If the universe were perfectly uniform, local measurements would match cosmic microwave background predictions. But uniformity is an assumption, not a fact. The cosmological principle states the universe looks roughly the same everywhere on large scales. This principle underlies lambda, cold dark matter cosmology. Without it, calculations become impossibly complicated. Different regions would need different equations. But what if the principle only holds approximately? What if large-scale structure includes variations big enough to matter? The KBC void challenges the cosmological principle. A 2 billion light-year underdensity isn't small scale. It's a significant fraction of the observable universe's diameter. If such structures exist, the universe is lumpier than standard cosmology assumes. Here's where it connects to the Hubble tension. The cosmic microwave background predicts expansion rate, assuming uniformity. That prediction should match measurements everywhere if the assumption holds. But if we live in a void, our local measurements sample non-uniform space. The void makes expansion appear faster here than the average elsewhere. The cosmic microwave background gives the average. Local measurements give the void-specific value. Both are correct within their contexts. Think of Earth's climate. Global average temperature tells you one thing. Local weather tells you something else. You need both to understand the full picture. Similarly, cosmic microwave background gives cosmic average expansion. Local observations give regional expansion. The mismatch reveals structure. Some researchers have tried using cosmic microwave background data to constrain local voids. They look for patterns indicating we're in an underdense region. The results are suggestive but not conclusive. The CMB's resolution limits how well it can detect nearby structures. By the time photons reach us, they've traveled so far that local details are blurred. Better evidence comes from combining cosmic microwave background data with galaxy surveys. The CMB provides initial conditions. Galaxy distributions show how those conditions evolved. Comparing the two reveals whether structure grew faster or slower than standard cosmology predicts. In our region, structure appears to have evolved into an underdensity. Whether this happened through normal processes or requires modified physics remains debated, but the cosmic microwave background itself contains no contradictions. It accurately represents the early universe and predicts the average expansion rate. The puzzle only appears when comparing its predictions to local measurements. That puzzle isn't a failure of the cosmic microwave background. It's evidence that local conditions differ from cosmic averages. Some stars pulse like cosmic lighthouses. Cepheid variables swell and shrink with clockwork regularity, growing brighter as they expand, dimmer as they contract. The rhythm depends on the star's true brightness. Brighter Cepheids pulse more slowly, dimmer ones pulse faster. This relationship, discovered by Henrietta Swan Leavitt in 1912, gave astronomers the first reliable way to measure cosmic distances. Here's how it works. Observe a Cepheid variable. Measure its pulsation period. That period tells you its absolute luminosity, how much light it truly emits. Measure its apparent brightness, how bright it looks from Earth. The difference between absolute and apparent brightness reveals distance. Bright objects appear dim when far away. The relationship is precise and mathematical. The challenge is finding Cepheids. They're rare, enormous yellow supergiants late in their stellar lives. Only a few thousand exist in the Milky Way. In distant galaxies, individual stars blur together. Seeing a single Cepheid millions of light-years away requires the Hubble Space Telescope or better. Yet Cepheids are essential for the cosmic distance ladder. They're bright enough to see in nearby galaxies, but rare enough to identify individually. They bridge the gap between distances measured by parallax and distances measured by other methods. The supernova H0 for the Equation of State project, abbreviated SH0ES, has spent decades observing Cepheids in galaxies where Type Ia supernovae have also appeared. Type Ia supernovae are exploding white dwarf stars. They're incredibly bright, briefly outshining entire galaxies. More importantly, they're remarkably consistent in peak brightness. This makes them standard candles for measuring vast distances. But they need calibration. Here's where Cepheids come in. Find a galaxy containing both Cepheids and a Type Ia supernova remnant. Use Cepheids to measure the galaxy's distance precisely. This calibrates the supernova's absolute brightness. Repeat this for multiple galaxies. Now you know how bright Type Ia supernovae truly are. Then observe distant Type Ia supernovae where Cepheids are too faint to detect. Their apparent brightness gives distance. Combined with redshift showing recession velocity, you can calculate the Hubble constant. Adam Rees has led this effort for years. His team has measured over 1,000 Cepheids in numerous galaxies. They've observed dozens of Type Ia supernovae. The precision is extraordinary. Uncertainties below 2%. When the James Webb Space Telescope became operational, Rees used it to double-check Hubble Space Telescope measurements. Webb's infrared vision cuts through dust. Its sharper resolution separates crowded stars. If earlier measurements had errors from confusing overlapping stars, Webb would reveal them. The results confirmed the earlier work. The Hubble constant remains 73 kilometers per second per megaparsec. The tension persists. Critics have questioned whether Cepheid measurements suffer from systematic errors. Maybe crowding affects brightness measurements in ways not accounted for. Maybe dust absorption is more complex than assumed. Maybe Cepheids in different environments have slightly different properties. Researchers have checked these possibilities rigorously. They've observed Cepheids in different types of galaxies. They've measured dust extinction using multiple wavelengths. They've looked for any trend that could explain the high Hubble constant values. Nothing emerges. The measurements appear robust. But here's the critical point. Cepheids only reach about 130 million light-years. Beyond that, they're too faint. The cosmic distance ladder relies on them only for nearby galaxies. Those nearby galaxies all sit within the KBC void. Every Cepheid used to calibrate Type Ia supernovae exists in the underdense region. If the void inflates local expansion measurements, Cepheids would show that inflation. They're measuring real expansion rates, just expansion rates within a special location. Type Ia supernovae extend further, out to billions of light-years. Some lie beyond the void's edge, but they're calibrated using nearby supernovae in Cepheid-containing galaxies. If the calibration is done inside the void, that void-specific expansion rate gets propagated to distance measurements. This doesn't make the measurements wrong, it makes them context-dependent. Distance measurements assume the expansion rate measured nearby applies everywhere. If it doesn't, if we're in a region expanding faster than average, then distances calculated using that rate will be systematically biased. The solution isn't to throw out Cepheid measurements. It's to recognize their limitations. They excellently measure local structure. They accurately reveal expansion in our cosmic neighborhood, but they can't directly measure global average expansion. For that, we need methods sampling the entire universe, like the cosmic microwave background or baryon acoustic oscillations at high redshift. Science thrives on disagreement, competing theories, contradictory measurements, unexpected results. These drive progress. But there's a difference between healthy debate and existential crisis. The Hubble tension crossed that line around 2015. Before then, uncertainties were large enough that different measurements could plausibly agree within error bars. Expansion rate between 67 and 73. Could be 70. Could be 72. Hard to say definitively. But technology improved. The Planck satellite delivered cosmic microwave background data with unprecedented precision. The Hubble Space Telescope observed hundreds of Cepheids in dozens of galaxies. Supernova surveys catalogued thousands of explosions at various distances. Error bars shrank. The measurements stopped overlapping. By 2018, the significance exceeded 3 sigma, odds of this being random variation, about 1 in 400. That's when researchers started using the word crisis. By 2019, 5 sigma, odds of random variation, 1 in 3.5 million. In particle physics, 5 sigma is the discovery threshold. If measurements differ by 5 sigma, you've found something real. In cosmology, 5 sigma disagreement between fundamental measurements means something is deeply wrong. Careers have been built trying to resolve this. Theorists propose elaborate modifications to cosmology. Early dark energy appearing briefly after the Big Bang, then vanishing. Time-varying dark energy that changes properties over cosmic history. Modifications to general relativity affecting large-scale gravity. Extra-relativistic particles influencing early universe dynamics. Interactions between dark matter and dark energy. Each proposal must be tested against multiple datasets. Cosmic microwave background fluctuations. Large-scale galaxy distribution. Primordial element abundances. Gravitational lensing observations. Cluster counts. Most proposals fail one or more tests. They resolve the Hubble tension but break something else. The standard lambda cold dark matter model succeeds because it fits everything. Well, it fit everything until the Hubble tension emerged. Experimentalists have checked equipment obsessively. Could Hubble Space Telescope have subtle systematic errors? Could the Planck satellite's calibration be slightly off? Could atmospheric distortion affect ground-based supernova observations in unexpected ways? Thousands of hours of analysis found nothing. The James Webb Space Telescope was supposed to settle the question. If Hubble Space Telescope measurements had errors, Webb would reveal them. Webb's superior resolution and sensitivity would either confirm or refute the 73 value. Instead, Webb confirmed it. Precise agreement with Hubble's measurements. No evidence of systematic error. The crisis deepened. Some researchers suggested the solution requires abandoning cherished assumptions. Maybe the cosmological principle is wrong. Maybe the universe isn't uniform on large scales. Maybe our observable region is special in some way. These ideas are uncomfortable. They feel like giving up on a century of progress. The cosmological principle emerged in the 1920s as humanity realized we're not at the universe's center. Earth orbits an ordinary star in an ordinary galaxy in an unremarkable location. Abandoning this principle feels like retreating to medieval geocentrism. But science follows evidence, not philosophy. If observations show the universe is less uniform than assumed, we must accept that. The KBC void provides exactly such evidence. It's not a small local irregularity, it's a massive structure affecting a significant volume of space, and we happen to live inside it. The coincidence bothers people. Why would Earth sit in such a special location? The anthropic answer is that observers must exist somewhere, and maybe voids offer conditions favorable to life. Lower density might mean fewer galaxy mergers, less radiation, more stable environments for complex chemistry. This is speculation, but it's not absurd speculation. The void explanation also appeals because it requires no new physics. Voids exist, their dynamics are well understood. They affect measurements in precisely the ways observed. No exotic particles, no modified gravity, no early dark energy, just standard cosmology applied carefully, accounting for local structure. Yet resistance remains. Some scientists find the void explanation unsatisfying. If we're in a void, does that mean lambda cold dark matter is still correct? Or does it mean the model needs revision to allow larger structures? The answer is subtle. Lambda cold dark matter correctly describes average cosmic evolution. It successfully predicts the cosmic microwave background. It explains structure formation and matter distribution. But it may underestimate variance at large scales. Computer simulations of structure formation use limited volumes. They can't simulate the entire observable universe at high resolution. Maybe simulations miss rare but real structures like the KBC void. Maybe voids this large are improbable but not impossible. Maybe our understanding of structure formation has small errors that compound over cosmic scales. Resolving the Hubble tension won't come from a single observation. It requires synthesizing evidence from multiple sources, galaxy surveys mapping the void's extent, bulk flow measurements tracking matter motion, baryon acoustic oscillations revealing expansion history at different locations, supernovae distances reaching beyond the void's edge. The data is coming. Within a decade, we'll know whether the void explanation holds. If it does, the crisis ends. If it doesn't, the mystery deepens. Wrap your mind around this scale. 2 billion light-years from edge to edge. A sphere so vast that light takes 2 billion years to cross it. 600 megaparsecs in astronomical units. For context, the Milky Way's diameter is 100,000 light-years. The void is 20,000 times wider. The local group, containing the Milky Way, Andromeda, and dozens of dwarf galaxies, spans 10 million light-years. The void is 200 times wider. The Laniakea supercluster, our galaxy's ultimate gravitational home, measures 500 million light-years across. The void is 4 times wider. This is not a small cosmic feature. It's one of the largest structures known to exist. Only a few voids exceed it in size. The Boötes void, discovered in 1981, spans 330 million light-years. Called the Great Nothing, it's nearly spherical and contains far fewer galaxies than expected. The Eridanus void reaches 1.8 billion light-years across. The KBC void competes with these supervoids for the title of largest known emptiness. But there's a crucial difference. We live inside the KBC void. From inside, measuring dimensions is challenging. Imagine standing in a forest, trying to determine where the forest ends. You can count nearby trees. You can notice when tree density decreases. But pinpointing exact boundaries requires surveying vast areas and analyzing density gradients. Cosmologists do this with galaxies instead of trees. They divide space into spherical shells at increasing distances. They count galaxies in each shell. They calculate average density for each shell. When density rises above a certain threshold, you've exited the void. Current measurements place the void's edge roughly 1 billion light-years away in most directions. But there's uncertainty. Maybe it's 800 million light-years in some directions. Maybe 1.2 billion in others. Voids aren't perfect spheres. They have irregular boundaries shaped by surrounding structures. The local sheet, a concentration of galaxies, including the Milky Way, forms one boundary of the void. This sheet acts like a wall, a denser region marking where the void ends. On the opposite side, other superclusters define the far edge. The void's center is also uncertain. Initial estimates placed it somewhere within a few 100 million light-years of the Milky Way. But determining exact center position requires mapping the void's full three-dimensional shape. That means surveying galaxies in all directions to multiple billions of light-years distance. Projects like the Sloan Digital Sky Survey and the 2-micron All-Sky Survey have done much of this work, but gaps remain. Some sky regions are obscured by our galaxy's dust. Some are undersampled due to limited observation time. New surveys will fill these gaps. What's clear is that the void contains far less matter than average space. Estimates range from 15 to 50% below cosmic mean density. The exact value depends on where you measure. Near the center, density might be 40% below average. Near the edges, maybe only 20%. This gradient matters for understanding void dynamics. A steeper gradient means stronger gravitational pull from outside. Matter would evacuate faster. The expansion rate distortion would be larger. Mapping this gradient precisely will help quantify the void's impact on the Hubble constant. The void also isn't empty in an absolute sense. It contains the Milky Way, obviously. It contains Andromeda, 30-odd, smaller local group galaxies. It includes much of Laniakea supercluster, which has over 100,000 galaxies. But, compared to a typical region of space that size, it's underpopulated by 20%. Imagine a city where every fifth building is missing. The city still functions. It still has roads, infrastructure, activity, but it's noticeably sparser than neighboring cities. That's the KBC void, still full of galaxies, just not as full as it should be. The formation history of such a void is complex. Standard cosmology says large voids form from small density fluctuations in the early universe. Slightly underdense regions expand faster than average. Matter flows from them toward denser regions. Over billions of years, the underdensity grows. But making a void as large as the KBC requires starting conditions that are statistically rare. The initial fluctuations must be large-scale and perfectly phased. Random quantum variations during inflation, the universe's earliest exponential expansion, should produce such fluctuations occasionally. But lambda cold dark matter calculations suggest voids this large should be exceptionally uncommon. This is the tension within the tension. The void potentially explains the Hubble tension, but the void's existence itself creates a different tension with standard cosmology. Resolving one problem reveals another. The universe began almost perfectly smooth. Almost quantum fluctuations during inflation created tiny density variations, 1 part in 100,000. Some regions had slightly more matter, others slightly less. These variations were random, like static on an old television. Gravity amplified them. Dense regions attracted more matter. They grew denser. Underdense regions lost matter to their denser neighbors. They grew emptier. This is gravitational instability, the fundamental process shaping cosmic structure. In the first few 100 million years, the densest fluctuations collapsed into the first stars. Their gravity pulled in surrounding gas. The stars clustered into proto-galaxies. Proto-galaxies merged into galaxies. Galaxies grouped into clusters. Clusters connected through filaments. By 1 billion years after the Big Bang, large-scale structure was recognizable. The cosmic web had formed. Long filaments of galaxies threading through space. Massive clusters where filaments intersect. And voids, the spaces between filaments. Think of soap foam. Galaxies concentrate on bubble surfaces. Voids occupy bubble interiors. This foam-like structure emerged naturally from gravity acting on initial fluctuations. But here's the key point. Voids aren't static. They continue evolving. A young void, say 2 billion years old, contains scattered galaxies slowly drifting toward the edges. Gravity from surrounding filaments pulls them outward. The void's interior empties gradually. By 5 billion years, the void is larger and emptier. Galaxies have migrated to the boundaries. Some have left the void entirely. The density contrast between void, interior, and surrounding structures has grown. By 10 billion years, the void is vast. Its interior contains very few galaxies. Most matter has evacuated. The density might be half the cosmic average or less. This process continues indefinitely. Voids keep growing. The universe's accelerating expansion helps. Dark energy drives expansion faster over time. In dense regions, gravity counteracts dark energy, keeping structure bound. In voids, there's insufficient gravity to resist. The expansion accelerates without opposition. This makes voids expand faster than the overall universe. Eventually, voids will dominate the cosmic volume. Trillions of years from now, the universe will be mostly empty space with sparse islands of matter, but we're not there yet. At the current cosmic age of 13.8 billion years, voids occupy about 80% of space but contain only about 20% of matter. They're underdense but not evacuated. The KBC void appears to be a mature void. It's been growing for most of cosmic history. Its size suggests it started from a large-scale fluctuation in the early universe. The exact formation mechanism depends on cosmological parameters. In standard lambda cold dark matter, structures grow bottom-up. Small fluctuations collapse first. They merge into progressively larger structures. This naturally produces voids as the spaces between collapsed regions. But growing a void as large as the KBC requires special initial conditions. The fluctuation must be large-scale to begin with. Random chance produces such fluctuations occasionally. Inflation's quantum jitter creates all scales of variation. Most are small, but rare large-scale fluctuations occur. Alternative theories change the story. Modified Newtonian dynamics, known as MOND, alters gravity at low accelerations. Under MOND, structure grows faster on certain scales. Neutrino hot dark matter models include extra neutrino species that damp structure growth differently. These models can produce large voids more readily than lambda cold dark matter. Whether standard cosmology or alternatives better explain the KBC void remains open. What's certain is that voids form naturally from initial conditions. They grow through well-understood dynamics. They're expected features of cosmic structure. The question isn't whether voids exist, it's whether voids as large as the KBC should exist. And whether finding ourselves in one is coincidence or indicates something deeper about observability. The Milky Way doesn't float alone. We're part of a vast, flat structure called the local sheet. This concentration of galaxies extends hundreds of millions of light years. It's shaped like a pancake, thin in one dimension and wide in the other two. Dozens of galaxy groups inhabit this sheet: the local group, the Maffei group, the NGC 3073 group. Each contains multiple galaxies bound by mutual gravity. The sheet itself represents a higher level of organization. These groups move together, flowing in response to large-scale gravitational fields. The local sheet forms one boundary of the local void, a smaller emptiness within the larger KBC void. Think of nested structures. The KBC void is the largest scale, 2 billion light-years across. The local void is smaller, maybe 150 million light-years wide. The local sheet separates these voids from denser structures beyond. This arrangement tells us about how structure formed. Voids grow by evacuating matter toward their edges. That matter doesn't vanish. It accumulates at boundaries, forming sheets and filaments. The local sheet is such an accumulation. Matter that once filled the local void now concentrates in the sheet. Measurements show the sheet moving away from the local void center. The velocity is substantial, about 260 kilometers per second. That's nearly 600,000 miles per hour. This outward motion is void evacuation in action. The entire sheet, containing billions of stars in thousands of galaxies, flees the emptiness. But the sheet isn't moving uniformly. Different parts have different velocities. Gravitational interactions with neighboring structures create complex motions. The result is that the sheet stretches and distorts as it evacuates. Over time, it will disperse. Individual galaxy groups will follow their own trajectories. Some will join nearby superclusters. Others will drift into intergalactic space. Billions of years from now, the local sheet might not exist as a coherent structure. For now, it marks a transition zone. On one side, the local void's low density. On the other, average cosmic density or denser regions. Crossing from void to sheet, galaxy counts increase noticeably. This boundary isn't sharp. There's no wall where galaxy density suddenly jumps. Instead, there's a transition region, perhaps 50 million light-years wide, where density gradually rises. But the effect is real. Stand in the sheet and look toward the void, you see relatively few galaxies. Look away from the void, you see many more. This asymmetry has implications. If astronomers only surveyed in one direction, they might miss the void entirely. Comprehensive all-sky surveys are essential for detecting large-scale structures. The local sheet also influences the Milky Way's motion. Our galaxy isn't just orbiting within the local group. The entire local group participates in the sheet's bulk motion. We're being carried along, evacuating the local void. This motion affects how we measure cosmic expansion. When we observe galaxies and measure their redshifts, we're implicitly comparing their velocities to ours. But our velocity includes the local sheet's evacuation flow. This creates systematic biases in expansion measurements. Galaxies in the direction we're moving appear slightly blue-shifted compared to the expansion prediction. Galaxies in the opposite direction appear slightly red-shifted. Averaged over all directions, the bias might cancel. But if measurements preferentially sample certain directions, the bias remains. Careful analysis must account for the local sheet's motion. Fortunately, we can measure this motion by observing the cosmic microwave background. Our movement relative to the CMB creates a dipole pattern, slightly hotter in the direction we're moving, cooler opposite. This measurement reveals the local group moves at 630 kilometers per second relative to the cosmic reference frame. That velocity includes the local sheet's bulk flow, plus contributions from larger structures like Laniakea supercluster. Subtracting these components allows astronomers to correct expansion measurements for local peculiar velocities, but uncertainties remain. The exact decomposition of our motion into different contributions depends on mapping surrounding structures precisely. As void boundaries are better defined, these corrections improve. Cosmic velocities are staggering. Earth orbits the star at 67,000 miles per hour. The star orbits the Milky Way's center at 490,000 miles per hour. The Milky Way orbits within the local group at around 200,000 miles per hour, but all these are small compared to the local group's bulk motion. We're fleeing the local void at approximately 600,000 miles per hour. That's 250 kilometers per second. Every second, our galaxy travels 250 kilometers away from the void's center. In an hour, 900,000 kilometers. In a day, 21.6 million kilometers. In a year, we traverse almost 8 billion kilometers of extra distance beyond what expansion alone would cause. This isn't expansion, it's motion through space. The difference is crucial. Cosmic expansion stretches space itself. Galaxies recede because the space between them grows. No galaxy actually moves through space during expansion, but peculiar velocities are different. These are real motions. Galaxies move through space, driven by gravitational forces. Dense structures pull galaxies toward them. Underdense structures push galaxies away. The void acts like negative mass, gravitationally repelling everything nearby. Measuring this velocity requires careful analysis. The raw observation shows the local group moving at 630 kilometers per second relative to the cosmic microwave background reference frame. This is called the CMB dipole. It creates a slight temperature difference between CMB photons approaching from ahead versus behind. But this total velocity includes multiple components. Part comes from the Milky Way's motion within the local group. Part comes from the local group's motion within the local sheet. Part comes from the local sheet's motion within larger structures. Each contribution must be separated. Astrophysicists do this by measuring velocities of nearby galaxies. If a galaxy shares our motion, it's part of the same bulk flow. If it moves differently, it responds to other influences. The Cosmic Flows Catalog contains peculiar velocity measurements for tens of thousands of galaxies. Analyzing this data reveals the layered structure of cosmic flows. The local void evacuation contributes about 250 kilometers per second to our total velocity. This isn't the fastest cosmic flow. The Great Attractor, a massive concentration of galaxies beyond the local void, pulls surrounding matter at speeds exceeding 1,000 kilometers per second. But the local void flow is significant because we're directly participating in it. Our motion affects every observation we make. When we measure a distant galaxy's redshift, we're measuring relative to a frame that's fleeing the void. The galaxy might be receding due to expansion at, say, 5,000 kilometers per second. But our own motion adds or subtracts from that depending on direction. If the galaxy lies in the direction we're fleeing, we measure slightly less redshift. If it lies opposite, we measure more. This creates directional biases in expansion measurements. Averaged over the whole sky, these biases partly cancel, but not entirely. The void's influence extends beyond just our peculiar velocity. The void's gravitational effect changes how expansion works nearby. Space expands slightly faster in the void's interior. This is separate from our motion. It's a modification to the expansion rate itself. Both effects, peculiar velocity and modified expansion, must be accounted for when interpreting observations. This is technically challenging. Many expansion measurements assume our peculiar velocity can be corrected using the CMB dipole. They subtract our motion and interpret the rest as pure expansion. But this assumes the expansion rate is uniform everywhere. If the void modifies the local expansion rate, this correction is insufficient. The void's expansion effect masquerades as additional peculiar velocity. Disentangling these effects requires modeling void dynamics in detail. The good news is that such models exist. The bad news is they depend on parameters like the void's exact size, density profile, and our position within it. Uncertainties in these parameters propagate into uncertainties in correcting measurements. Future observations will improve this situation. Larger samples of galaxies with measured peculiar velocities will map the flow field more accurately. Better measurements of galaxy distributions will pin down the void's properties. Simulations incorporating voids will predict observable signatures. Within a decade, the local velocity field will be understood well enough to make precise corrections. For now, we know we're fleeing the void at extraordinary speed. This motion is real, measurable, and consequential. It affects how we perceive the universe's expansion. Accounting for it properly is essential for resolving the Hubble tension. Sound in space. Before atoms existed, the universe rang with acoustic waves, not sound as we know it, no air to carry vibrations, but pressure waves in plasma, alternating compressions and rarefactions traveling at incredible speeds. This happened in the first 400,000 years, when the universe was a dense fog of charged particles and light. Protons, electrons, photons, all mixed together. The mixture behaved like a fluid. Denser regions had higher pressure. That pressure drove expansion, but gravity fought back, pulling matter together. The competition created oscillations. Imagine pressing a spring. Release it, and it bounces past equilibrium, compressing on the other side. Gravity and pressure did this cosmically. Overdense regions compressed under gravity until pressure pushed them apart. They expanded past equilibrium until gravity pulled them back. Each cycle took hundreds of thousands of years. The waves propagated outward from every initial density fluctuation. They traveled fast, about 58% of light speed. Not as fast as light because matter's inertia slowed them. Dark matter complicated the picture. It doesn't interact with photons. No pressure affects it. Dark matter responded only to gravity. So while normal matter and photons oscillated, dark matter stayed put at each fluctuation's center. This created a specific structure. At the origin point, a concentration of dark matter. Then a shell of normal matter and radiation at the distance the sound wave traveled. Then another shell further out from the next oscillation cycle. When atoms formed, everything changed instantly. Electrons and protons combined into neutral hydrogen. Photons decoupled from matter. The pressure supporting the sound waves vanished. The oscillations froze mid-cycle. Whatever pattern existed at that moment became permanent. The dark matter concentrations remained at the origins. The matter shells remained at the distances they'd reached. Over billions of years, gravity pulled additional material into these patterns. Galaxies formed preferentially at the overdense locations, both at the origin points and at the frozen sound wave shells. This left a signature. Galaxy clustering shows a slight preference for certain separation distances. Pairs of galaxies are more common at around 500 million light-years apart than at slightly smaller or larger distances. This is the baryon acoustic oscillation signal. It's subtle. The excess is only a few percent, but it's detectable with large enough galaxy samples. Surveys cataloging millions of galaxies reveal the pattern clearly. Why does this matter for measuring expansion? Because the separation distance is known precisely. The sound wave traveled for a specific time, at a specific speed. Physics determines both. We can calculate the distance the wave traveled before freezing. It was about 450,000 light-years at the time of freezing, but the universe has expanded since then. That distance has stretched by the same factor as everything else. Measuring what that distance looks like today tells us the total expansion factor. If we observe galaxies at various distances and measure the baryon acoustic oscillation scale at each distance, we trace the universe's expansion history. Closer galaxies show less expansion. Distant galaxies show more. The pattern reveals how expansion rate changed over time. This method doesn't require Cepheids or supernovae. It's independent of the cosmic distance ladder. It uses only geometry and the known physics of sound in the early universe. That makes it powerful for cross-checking other methods. And here's where the void enters. Baryon acoustic oscillations measure expansion between galaxies. If galaxies near us are evacuating the void, their motion adds to their redshift. The baryon acoustic oscillation distance appears slightly larger than it should based on expansion alone. This distortion is small but measurable. It varies with distance. Galaxies well within the void show maximal distortion. Galaxies beyond the void's edge show minimal distortion. By measuring baryon acoustic oscillations at different distances and comparing to predictions, astronomers can map the void's influence. This is exactly what Indranil Barnik did. He analyzed 20 years of baryon acoustic oscillation data from multiple surveys. The measurements showed systematic patterns consistent with a local void. The void model explained the data 100 million times better than a uniform model. This is compelling evidence. Baryon acoustic oscillations provide an independent test of the void hypothesis. They don't rely on Cepheids or supernovae distance measurements. They don't depend on cosmic microwave background predictions. They're pure geometry based on well-understood physics. And they support the conclusion, we live in a void, and that void affects our measurements. Astronomers need measuring sticks to map the cosmos. The baryon acoustic oscillation provides the perfect ruler. Its length is fixed by physics from the early universe. It never changes. It appears everywhere in the galaxy distribution, and it's calibrated by the most precise measurements we have. Think of it as a cosmic yardstick stretched across billions of light-years. When atoms formed 380,000 years after the Big Bang, sound waves froze at a specific distance from their origin points. That distance, called the sound horizon, was 450,000 light-years. Over the following billions of years, the universe expanded. The sound horizon expanded with it. Today, that same distance has stretched to roughly 500 million light-years. But here's the crucial insight. Every baryon acoustic oscillation signal throughout the universe stretched by the exact same factor. The ratio between then and now reveals total cosmic expansion. Measure this ratio at different cosmic epochs, and you trace expansion history. Galaxies at redshift 0.5 show the universe when it was 2/3 its current age. Their baryon acoustic oscillation scale appears smaller because less expansion occurred before their light reached us. Galaxies at redshift 1 show the universe at half its current age. Their scale appears even smaller. Plot these measurements across cosmic time, and you reconstruct how expansion evolved. The method is elegant. It requires no assumptions about star brightness or supernova physics. Just count galaxies. Measure their positions in 3 dimensions. Calculate clustering statistics. The baryon acoustic oscillation bump appears in the correlation function at the predicted scale. The precision depends on sample size. Survey 10,000 galaxies, and statistical noise obscures the signal. Survey 1,000,000 galaxies, and the bump becomes clear. Survey 10 million, and you measure the scale to percent-level precision. Modern surveys achieve this. The Sloan Digital Sky Survey mapped over 1,000,000 galaxies. The Baryon Oscillation Spectroscopic Survey extended this to higher redshifts. The Dark Energy Spectroscopic Instrument, abbreviated DESI, is measuring 15 million galaxy positions. These massive datasets reveal the baryon acoustic oscillation signal with extraordinary clarity. The scale varies smoothly with redshift, exactly as expansion predicts. But there's a complication. Measuring the scale requires knowing each galaxy's distance. Distance comes from redshift. Redshift has 2 components: cosmic expansion and peculiar velocity. A galaxy might have redshift 0.1 from expansion, but if it's moving toward us at 1,000 kilometers per second, peculiar velocity reduces the redshift slightly. Moving away increases it. These velocity effects blur the baryon acoustic oscillation measurement. Fortunately, peculiar velocities average out over large samples. Most galaxies aren't correlated in their motions. Random velocities in random directions cancel statistically. What doesn't cancel are systematic bulk flows. If a large group of galaxies moves coherently, their collective motion shifts the baryon acoustic oscillation scale. This is exactly what void evacuation does. Galaxies fleeing the void have systematic outward velocities. Their redshifts are enhanced in the direction we're moving. The baryon acoustic oscillation scale appears distorted along that direction. Different distortions appear perpendicular to our motion. By measuring these distortions, astronomers probe velocity fields. Redshift space distortions, as they're called, reveal how matter flows. In a uniform universe, these distortions have a specific pattern determined by gravity pulling matter into dense regions. In a void, the pattern changes. Matter flows outward instead of inward. The distortions flip side. 20 years of baryon acoustic oscillation measurements show exactly this signature. The pattern doesn't match uniform lambda-cold, dark matter predictions. It matches a model with a local void. The statistical confidence is overwhelming. But interpreting this requires careful modeling. The void's size, depth, and our position within it all affect the predicted distortion pattern. Researchers fit multiple parameters simultaneously: void radius, central density, density gradient, observer location. Each combination predicts a specific baryon acoustic oscillation signal. The best-fitting model has a void roughly 1 billion light-years in radius, 20% underdense, with Earth near the center. This model explains the data far better than alternatives. It predicts the observed Hubble tension magnitude. It matches bulk flow measurements. It aligns with direct galaxy count studies showing local underdensity. The standard ruler method, independent of other techniques, points to the same conclusion. We live in a void. That void distorts our measurements. Accounting for it resolves apparent contradictions. The beauty of this approach is its simplicity. No exotic physics required, no modifications to gravity, no new particles or fields, just standard cosmology applied carefully, recognizing that local conditions differ from cosmic averages. The baryon acoustic oscillation ruler measures both local and global properties. At high redshifts beyond the void, it measures average expansion. At low redshifts within the void, it measures void-modified expansion. Comparing the two, reveals the void's influence quantitatively. Future surveys will refine this. The Euclid space mission will map billions of galaxies across half the sky. The Vera Rubin Observatory will survey the entire southern sky repeatedly. These projects will measure baryon-acoustic oscillations to sub-percent precision across a wide range of cosmic epochs. Within a decade, the void's properties will be known definitively. Either the model holds up under scrutiny, or it fails. Either way, the standard ruler will provide the answer. Lambda cold dark matter has been cosmology's triumph for 3 decades. It explains the cosmic microwave background's temperature fluctuations. It predicts element abundances from the Big Bang. It describes how galaxies form and cluster. It accounts for gravitational lensing observations. It matches supernova data, showing accelerating expansion. Dozens of different observations, each testing different physics, all agree with the model. The success is remarkable. 6 parameters determine everything: the Hubble constant, matter density, dark energy density, the spectrum of initial fluctuations, 2 parameters describing those fluctuations' shape. From these 6 numbers, cosmologists calculate the entire universe's evolution from microseconds after the Big Bang to the present day. The model makes predictions that observations confirm repeatedly. It predicted the cosmic microwave background's 3rd acoustic peak before measurements detected it. It predicted the pattern of galaxy clustering at different scales. It predicted how fast structure grows over cosmic time. Every prediction matched reality, except for 2 problems: the Hubble tension and the KBC void. These aren't minor discrepancies. They challenge the model's foundations. The model assumes the universe is homogeneous and isotropic at large scales. Homogeneous means the same everywhere. Isotropic means the same in all directions. This is the cosmological principle, the assumption that we don't occupy a special location. Average the universe over a few 100 million light-years, and every region should look statistically identical. Same galaxy density, same matter distribution, same expansion rate. But the KBC void violates this. A 2 billion light-year underdensity is too large for the model's framework. At such scales, the universe should be uniform. Lambda cold dark matter's equations assume uniformity. They model the universe as a smooth fluid with small ripples. The ripples grow into galaxies and clusters, but they shouldn't grow into voids spanning billions of light-years. Computer simulations test this. Researchers run cosmological simulations starting from realistic initial conditions. They evolve the universe forward using lambda cold dark matter physics. They let gravity pull matter together over billions of simulated years. The results produce cosmic web structure. Filaments, clusters, and voids emerge naturally, but the voids are smaller. Typical simulated voids span a few 100 million light-years. Occasionally, a simulation produces a billion light-year void. But the statistics are clear. Voids as large as the KBC should be extremely rare. Some calculations suggest only 1 in 1,000 universe-sized volumes should contain such a void. Others say 1 in a million. Depending on assumptions, the probability ranges from unlikely to nearly impossible. Yet we apparently live in one. This is called the fine-tuning problem. Why do we find ourselves in such an improbable location? 3 possible answers exist. First, we're extraordinarily lucky. Rare events happen. Someone wins the lottery despite 1,000,000 to 1 odds. We happen to form in a rare giant void. This answer is unsatisfying but not logically impossible. Second, the simulations are wrong. Maybe lambda cold dark matter underestimates structure growth at large scales. Maybe the initial conditions weren't as smooth as assumed. Maybe some physics is missing that allows larger voids to form more easily. This would require modifying the model, not abandoning it entirely, but adjusting parameters or adding components. Early dark energy, modifications to the matter-power spectrum, or changes to how dark matter behaves might allow larger structures. Third, the cosmological principle is wrong. Maybe the universe isn't uniform at large scales. Maybe averaging over a few 100 million light-years isn't enough. Maybe true homogeneity only appears over tens of billions of light-years. If so, our observable universe shows significant variations. We happen to occupy an underdense region. Other regions are overdense. The average across everything might be uniform, but local patches differ substantially. This third option troubles cosmologists deeply. The cosmological principle isn't just convenience, it's philosophical bedrock. Copernicus taught us Earth isn't the center. Hubble taught us our galaxy isn't special. The principle extends this. Our cosmic neighborhood isn't special either. Abandoning it feels like regression, but philosophy must yield to evidence. If observations show large-scale inhomogeneity, we must accept it. The alternative is worse, clinging to beautiful theories that don't match reality. Lambda, cold, dark matter might be mostly correct. It works at most scales, but it might need adjustments for the largest structures, or it might need to acknowledge that statistical uniformity requires averaging over scales larger than our observable universe. Either way, the model faces challenges. The KBC void isn't explained by standard cosmology. It's a puzzle requiring a solution. What if Einstein was almost right, but not quite? General relativity has passed every test for over a century. It predicts gravitational waves detected by LIGO. It predicts black hole shadows imaged by the Event Horizon Telescope. It predicts light bending around massive objects, confirmed thousands of times. But there's a catch: dark matter, dark energy. These components dominate the universe, yet we've never directly detected either. They're inferred from gravity behaving differently than visible matter suggests. What if gravity itself works differently at cosmic scales? Modified Newtonian dynamics, abbreviated MOND, proposes exactly this. At high accelerations like Earth's surface, gravity follows Newton's and Einstein's predictions exactly. But at extremely low accelerations, the kind experienced at galaxy edges or between galaxies, gravity becomes stronger than predicted. This modification eliminates the need for dark matter in galaxies. Rotation curves flatten without invoking invisible mass. Dwarf galaxies behave correctly without dark matter halos. Empirical relations between visible matter and dynamics emerge naturally. MOND has been remarkably successful at galaxy scales, but extending it to cosmology is difficult. The theory needs dark matter for cluster dynamics. It struggles to explain gravitational lensing observations. The cosmic microwave background doesn't fit without significant modifications. Pavel Krupa and colleagues have developed a cosmological version incorporating neutrinos. Their model includes 3 standard neutrino types plus 1 extra sterile neutrino. This neutrino has a specific mass, 11 electron volts. With this addition, the modified gravity framework can reproduce many cosmological observations. Crucially, it forms large voids more easily than lambda-cold dark matter. The KBC void, improbable in standard cosmology, becomes natural in this framework. Structure grows faster at large scales. Initial fluctuations amplify differently. The result is a universe with more pronounced cosmic web features. Bigger voids, denser filaments, more extreme contrasts. This matches observations showing our local region is quite underdense. But the model has problems. It doesn't match all observations equally well. Some galaxy cluster measurements disagree with predictions. The model requires fine-tuned parameters to work. Many physicists find it less elegant than lambda-cold dark matter. There's also Occam's razor, which is simpler, modifying a successful gravity theory to avoid dark matter, or accepting that most matter is non-luminous. Most cosmologists favor the latter. Dark matter might seem exotic, but it's conceptually straightforward. Particles that don't emit light but do have mass. Modified gravity requires changing fundamental physics in ways that seem arbitrary. Yet the void evidence gives modified theories new life. If lambda cold dark matter can't easily produce the KBC void, maybe alternative frameworks can. If the Hubble tension persists despite considering the void, maybe gravity modifications explain the residual. The debate is ongoing. Recent papers compare predictions from different frameworks. Some support lambda cold dark matter with the void included. Others support modified theories. The data isn't yet precise enough to rule out either option. Bulk flow measurements might decide this. Lambda cold dark matter predicts specific flow patterns. Modified gravity predicts different patterns. The Cosmic Flows 4 catalog shows flows consistent with a large void but doesn't definitively favor one theory. The neutrino hot dark matter model, combining MOND with sterile neutrinos, predicts bulk flows exceeding 400 kilometers per second at distances of 300 million light-years. Observations match this, but lambda cold dark matter with a void can also produce such flows. Future measurements with larger galaxy samples will test these predictions more stringently. Within a few years, the bulk flow field will be mapped accurately enough to distinguish models. For now, alternative gravity theories remain viable. They're not mainstream. Most cosmologists still work within lambda cold dark matter, but the KBC void gives alternatives renewed motivation. If the void is real and standard cosmology struggles to explain it, modified theories deserve serious consideration. Science progresses by testing alternatives. Dismissing ideas because they're unfamiliar is lazy. Keeping an open mind while demanding rigorous evidence is the correct approach. The void might ultimately vindicate standard cosmology, or it might require something new. Either way, exploring alternatives helps clarify what's true. How old is everything? Cosmologists thought they knew. 13.8 billion years, give or take a few tens of millions. The cosmic microwave background reveals this age. Temperature fluctuations encode information about how long the universe has been expanding and cooling. The calculation assumes lambda cold dark matter cosmology. It depends on the Hubble constant. Higher expansion rate means the universe expanded to its current size faster. Faster expansion means younger age. Lower expansion rate means slower growth. Slower growth means older age. The cosmic microwave background method gives a Hubble constant of 67, yielding 13.8 billion years. The local measurement method gives 73, yielding 13.0 billion years, 800 million years of difference. That's significant. 800 million years is enough time for entire generations of stars to form, live, and die. It's enough time for galaxies to undergo major mergers. It's enough to change structure formation predictions substantially. Which age is correct? Both, possibly. If we live in a void expanding faster than average, the age depends on what you're asking. The universe's global age, averaged everywhere, might be 13.8 billion years, but the local age, measured by tracking expansion within the void, might be 13 billion years. These aren't contradictory. They're measuring different things. But there's a complication. Some objects appear older than 13 billion years. The oldest known stars, found in globular clusters, seem to be around 13.2 billion years old. Radioactive dating of elements provides independent age estimates, also around 13 billion years. If the void explanation lowers the universe's age to 13 billion, it creates problems. You can't have stars older than the universe. One solution is that age estimates have uncertainties. Maybe the oldest stars are actually 12.8 billion years old. Maybe element dating has systematic errors. These uncertainties might accommodate the lower age. Another solution is that the void explanation doesn't change the global age. The universe is still 13.8 billion years old everywhere. Only our measurements of expansion rate differ. The age remains consistent because global expansion, not local expansion, determines age. This depends on technical details about how expansion history is reconstructed. A third possibility is more radical. Maybe the universe's age varies by location. If the void formed early and has been evacuating for most of cosmic history, its interior might have experienced slightly different expansion history. Time itself, in a sense, could have passed differently. General relativity allows this. Strong gravitational fields affect time's passage. Clocks run slower in deep gravity wells. They run faster in voids. Integrated over billions of years, these differences might accumulate. Matter in the void's interior could be slightly younger than matter outside. This is highly speculative. The effect would be tiny, probably too small to matter, but it illustrates how even fundamental concepts like age become subtle in general relativity. The practical issue is that cosmological ages are model-dependent. Change the model, change the age. If lambda cold dark matter with uniform expansion is correct, the age is 13.8 billion years. If a void model is correct, calculations need adjustment. The adjustment might raise or lower the age depending on details. Resolving this requires better understanding of the void's properties. How deep is the underdensity? How has it evolved over time? What was the expansion history within the void versus outside? These questions have answers in principle. Observations at different redshifts sample different cosmic epochs. Measuring expansion rate as a function of time reveals the history. Baryon acoustic oscillations at various distances do exactly this. The data should show if expansion within the void has been consistently faster or if the difference only appeared recently. Early results suggest the void has existed for billions of years. The underdensity isn't new. It's been growing throughout cosmic history. If so, expansion within the void has been enhanced for a long time. That would lower the local age estimate systematically. But the global age, measured by the cosmic microwave background from the entire universe, remains 13.8 billion years. We just happen to live in a region where local clocks ran slightly faster. This might sound like science fiction, but it's standard general relativity. Gravity affects time. Different gravitational environments have different time evolution. The void is a real gravitational environment producing real effects. Accounting for those effects is essential for accurate cosmology. Rivers of galaxies flow through space, not metaphorically, literally. Vast streams of matter moving coherently across hundreds of millions of light years. These are bulk flows, the collective motion of structures too large to be bound by their own gravity. A single galaxy's motion is relatively simple. It orbits within its local group. The group orbits within a cluster. The cluster participates in supercluster dynamics. Each level adds velocity components, but beyond a few hundred million light-years, coherent motion shouldn't exist. Standard cosmology predicts peculiar velocities decrease with increasing scale. Average the motion of many galaxies, and random components cancel. Only expansion remains. By 300 million light-years, bulk flows should drop below 100 kilometers per second. By 500 million light-years, they should be negligible. Observations disagree. Multiple studies find bulk flows exceeding 400 kilometers per second at scales of 300 million light-years. Some measurements suggest 500 kilometers per second or more. These are substantial velocities. They indicate massive structures pulling on enormous volumes of space, or pushing on them. The Cosmic Flows 4 catalog contains peculiar velocity measurements for over 50,000 galaxies. The data shows clear patterns. Matter flows from underdense regions toward overdense regions. It flows from voids toward superclusters. The flows aren't random, they're highly structured. One of the strongest flows points toward the Shapley supercluster, the most massive structure in our cosmic neighborhood. This supercluster, located 650 million light-years away, contains thousands of galaxies. Its gravitational pull affects motion across 1 billion light-years. Another significant flow evacuates the local void. Galaxies in our region move outward at speeds approaching 300 kilometers per second. This flow contributes to the larger scale pattern pointing towards Shapley. The KBC void produces an additional flow component. Being much larger than the local void, it influences motion over greater distances. Galaxies within 1 billion light-years of the void's center participate in the evacuation. The velocity depends on position. Near the center, evacuation is slower. The gravitational gradient is weaker. At intermediate distances, evacuation is fastest. The pull from outside is strong, but galaxies haven't yet escaped. Near the edges, velocities decrease again as galaxies enter denser regions where local gravity dominates. This pattern matches observations. Bulk flow measurements show exactly the velocity profile expected for a large void. The magnitude, spatial variation, and direction all align with the KBC void model. But there's controversy. Some researchers argue the observed bulk flows are too large for lambda-cold dark matter. Even accounting for voids, the velocities exceed predictions. This suggests either the voids are larger and deeper than models allow, or something else generates the flows. One alternative is modified gravity. Under Mond-based cosmology, bulk flows grow stronger. Matter responds more strongly to density contrasts. The observed 400 km per second flows become natural. Lambda-cold dark matter predicts weaker flows. The discrepancy might indicate the model needs adjustment. Another alternative invokes early universe physics. If initial fluctuations were larger than assumed, structure would have grown faster. Bulk flows would be stronger today. This could resolve the tension without modifying gravity. Distinguishing these explanations requires precise measurements. The velocity field must be mapped accurately across vast volumes. Distance errors propagate into velocity errors. A 10% distance uncertainty translates to 10% velocity uncertainty. Current measurements have errors around 15 to 20%. That's barely sufficient to detect bulk flows, but insufficient to constrain models tightly. Future surveys will improve this. The Vera Rubin Observatory will measure billions of galaxies' positions. Distance estimates will improve from larger samples. The Nancy Grace Roman Space Telescope will observe galaxies at higher redshifts, tracing flow evolution over cosmic time. Within a decade, bulk flow measurements will have 5% precision. That's enough to distinguish lambda-cold dark matter from modified gravity. It's enough to measure void properties accurately. It's enough to test whether observed flows match predictions quantitatively. For now, bulk flows provide strong evidence for the KBC void. The velocity patterns align with void evacuation. The magnitudes are consistent with a 2 billion light-year underdensity. The data supports the conclusion that we live in a large void affecting motion over enormous scales. These cosmic currents also affect expansion measurements. When we measure a galaxy's redshift, we're measuring expansion plus peculiar velocity. If the galaxy participates in a bulk flow toward or away from us, its redshift is shifted. This creates systematic biases if not corrected. Bulk flows toward us, reduce apparent expansion. Flows away, increase it. The KBC void evacuation flow predominantly moves galaxies away from us in most directions. This enhances measured expansion rates systematically. It's another mechanism by which the void inflates the local Hubble constant. Correcting for bulk flows requires knowing the velocity field precisely. Current corrections use models based on observed galaxy distributions. These models predict flow patterns that are then subtracted from redshift measurements. But if the models are incomplete or inaccurate, residual biases remain. The void must be included in these models. Ignoring it leads to incorrect flow predictions and incomplete corrections. Including it improves agreement between different measurement methods. Stand back far enough, and the universe resembles foam. Dense filaments trace bubble boundaries. Clusters mark where filaments intersect. Voids occupy bubble interiors. This cosmic web structure emerged naturally from gravity acting on initial fluctuations. But it's not what early cosmologists expected. In the 1970s, astronomers thought galaxies distributed uniformly. Large-scale surveys proved otherwise. The first three-dimensional maps showed shocking patterns. Long filaments of galaxies extending hundreds of millions of light-years. Enormous voids nearly empty of bright galaxies. The Sloan Digital Sky Survey revealed this structure in stunning detail. Filaments connect across the entire surveyed volume. Voids between them contain far fewer galaxies. The overall pattern does resemble soap bubbles packed together. Each void is a bubble. Filaments are where bubbles touch. Clusters are where multiple bubbles meet. This structure tells us about how the universe evolved. Dense regions collapsed first. They pulled matter from surroundings. Underdense regions lost matter. The contrast amplified over time. By now, 13.8 billion years later, the separation is stark. Most galaxies live in filaments and clusters. Most volume is void. Roughly 80% of space qualifies as void by density criteria. But this space contains only 20% of galaxies. The remaining 20% of space, the dense regions, contains 80% of galaxies. This extreme clustering wasn't expected. Simple gravity pulling on small random fluctuations should produce gentler variations. Why did structure become so extreme? Part of the answer is dark matter. It doesn't feel radiation pressure. It collapses more easily than normal matter. Dark matter formed structures first. Normal matter fell into those structures later. This two-stage process amplified contrasts. Another factor is time. The universe is old. Gravity has had billions of years to work. Even small initial contrasts amplify exponentially when given enough time. The rich get richer. Dense regions attract more matter, becoming denser. Voids lose matter, becoming emptier. Runaway growth produces extreme results. Dark energy contributes too. By accelerating expansion, it stretches voids faster than gravity can fill them. Without dark energy, voids would eventually collapse. Surrounding matter would fall in, filling the emptiness. With dark energy, voids expand faster than matter can cross them. They're permanently evacuated. The cosmic web also has dynamics. It's not static. Filaments shift, clusters merge, voids grow. The entire structure evolves continuously. Galaxies flow along filaments like cars on highways. They enter clusters where filaments intersect. Some get trapped by cluster gravity. Others pass through, continuing along filaments. This traffic creates complex velocity patterns. The web channels motion. Instead of galaxies moving randomly, they follow preferred paths. Voids repel matter along pressure gradients. Filaments guide matter toward clusters. The result is organized flow on enormous scales. Our position in this web matters. The Milky Way sits in a relatively thin filament, the local sheet. This sheet forms one boundary of the local void. Beyond the sheet, denser structures like the Virgo cluster and Shapley supercluster pull on us gravitationally. The KBC void pushes from the opposite direction. We're caught in the middle, subject to conflicting influences. This location affects our observations. Looking toward the void, we see relative emptiness. Looking toward Shapley, we see rich galaxy fields. The cosmic microwave background appears slightly colder toward the void and warmer toward Shapley. These anisotropies reflect real structure around us. They're not measurement errors or coincidences. Mapping the web precisely is crucial for cosmology. The distribution of voids and filaments tests structure formation theory. Lambda-cold dark matter predicts specific statistical properties. The web should have certain size distributions of voids and filaments, certain connectivity patterns, certain mass distributions. Observations mostly match these predictions. The web looks statistically similar to simulated cosmic webs, but exceptions exist. The largest voids and largest clusters are bigger than simulations typically produce. The KBC void is one such exception. So is the Shapley supercluster. These extremes challenge the model. Maybe they're just rare statistical fluctuations. Or maybe structure formation works slightly differently than standard cosmology assumes. The Webb also reveals dark matter distribution indirectly. Where galaxies cluster, dark matter clusters. Where voids exist, dark matter is scarce. Gravitational lensing maps mass directly, confirming this picture. Dark matter follows the cosmic web. Future observations will map the web in unprecedented detail. The Euclid mission will survey billions of galaxies across half the sky. Vera Rubin Observatory will repeatedly image the entire southern sky. These projects will reveal cosmic web structure from nearby to redshifts beyond 1. Comparing web properties at different cosmic epochs tests how structure evolved. Did the web form early or late? Did voids grow steadily or rapidly? Does their growth match predictions? These questions have answers waiting in data. The cosmic web isn't just background. It's the fundamental organization of matter. Understanding it is essential for understanding cosmology, and our location within it affects every observation we make. The evidence is strong but incomplete. The KBC void hypothesis explains multiple observations. It resolves the Hubble tension. It matches bulk flow measurements. It aligns with galaxy distribution data. But definitive proof requires more. Several observations could confirm or refute the void. First, measure the Hubble constant beyond 3 billion light-years. If the void explanation is correct, measurements sampling space outside the void should give lower values. Expansion should appear slower beyond the void's edge. This is testable. The James Webb Space Telescope can observe Cepheid variables at greater distances than ever before. Its infrared sensitivity cuts through dust. Its resolution separates crowded stars. Observations are underway to measure Cepheids in galaxies 3 to 4 billion light-years away. If these distant measurements yield a Hubble constant near 67 instead of 73, the void explanation gains strong support. If they still give 73, the void hypothesis faces serious problems. Second, map the void's three-dimensional shape precisely. Current measurements show we're in an underdense region, but the exact boundaries remain uncertain. The void's center position isn't pinpointed. Its density profile needs better characterization. The Vera Rubin Observatory will help. Starting operations soon, it will photograph the entire southern sky every few nights. Over a decade, it will catalog 10 billion galaxies. This massive dataset will map large-scale structure with unprecedented precision. The void will stand out clearly in the distribution. Its size, shape, depth, and position will be measured accurately. These measurements will test predictions. The void should be roughly spherical, possibly elongated. It should have smooth density gradients, not sharp boundaries. We should be positioned within a few 100 million light-years of the center. If observations contradict these expectations, the model needs revision. Third, measure bulk flows at multiple scales and distances. The Cosmic Flows project continues gathering data. Each new measurement improves the velocity field map. The Nancy Grace Roman Space Telescope will revolutionize this. Launching around 2030, it will observe galaxies across enormous volumes. Its wide field of view covers areas 100 times larger than Webb's. It will measure millions of galaxies' distances and velocities. This data will trace bulk flows from our local neighborhood to billions of light-years away. The flow patterns should show void evacuation signatures, velocities pointing outward from the void's center, magnitudes decreasing with distance from the center, alignment with galaxy distribution under densities. If these patterns appear as predicted, the void model is confirmed. If they don't, we need different explanations. Fourth, detect the integrated Sachs-Wolf effect from the void. Cosmic microwave background photons traversing a void should lose energy climbing the gravitational hill. This creates a cold spot in the microwave background. The KBC void should produce exactly this signature. Calculations predict where the cold spot should appear and how strong it should be. Current cosmic microwave background maps from Planck show hints of the predicted cold spot, but the signal is noisy. Higher sensitivity observations would strengthen the detection. Future missions might improve measurements. Ground-based telescopes, like the Simons Observatory, are beginning observations. They'll map cosmic microwave background temperature and polarization with precision exceeding Planck's. If the void's integrated Sachs-Wolf signal becomes clear, it's powerful independent evidence. Fifth, compare baryon acoustic oscillation measurements at different distances. We discussed this earlier, but it deserves emphasis. The Euclid mission will measure baryon acoustic oscillations across half the sky, thousands of data points spanning from nearby to redshift 2. If the void model is correct, baryon acoustic oscillations measured within the void should show subtle distortions. The scale should appear slightly different than for measurements beyond the void. Detailed analysis will reveal these effects if they exist. The Dark Energy Spectroscopic Instrument is already collecting this data. 5 years of observations will provide statistics sufficient for percent-level measurements. Results are expected around 2028. These will either confirm the void hypothesis or rule it out. Sixth, look for void signatures in other cosmic structures. If the KBC void exists, perhaps others do too. Are there other observers in other voids experiencing similar Hubble tensions? Mapping multiple voids would reveal whether they're common or rare. It would test whether lambda cold dark matter underestimates large-scale structure. Surveys covering larger volumes will answer this. Projects like the Square Kilometre Array will map hydrogen gas across vast cosmic volumes. Gas traces voids just as galaxies do. The patterns will show whether our void is unique or representative. All these observations will arrive within a decade. By 2035, the data will be overwhelming. Either the void hypothesis survives scrutiny or it fails. Either way, cosmology advances. We'll understand our cosmic neighborhood better. We'll know whether the Hubble tension requires exotic physics or just careful accounting for local structure. The suspense is genuine. Science at its best. Dark energy dominates the universe. It comprises 68% of all mass energy. It drives accelerating expansion. Without it, gravity would slow expansion over time. Eventually, the universe would collapse. But dark energy prevents collapse. It pushes space apart with increasing strength as the universe grows. At least, that's the standard picture. Lambda, cold dark matter, models dark energy as Einstein's cosmological constant, a constant energy density filling space uniformly. As space expands, more space means more dark energy. This creates runaway expansion. The more space, the more dark energy. The more dark energy, the faster expansion. Faster expansion creates more space. The cycle continues indefinitely. This simple model fits most observations: supernova distances, cosmic microwave background fluctuations, large-scale structure growth, all match predictions for a cosmological constant with specific strength. But two tensions exist: the Hubble tension, and measurements suggesting dark energy might not be constant. Recent data from the Dark Energy Spectroscopic Instrument hints that dark energy's strength varies over time. The equation of state parameter, denoted W, might differ from -1. -1 means constant vacuum energy. Values differing from -1 mean time-varying dark energy. DESI's preliminary results suggest W might be around -0.999, close to constant, but not quite. If real, this has profound implications. Dark energy wouldn't be Einstein's cosmological constant. It would be a field that evolves, called quintessence. Such fields appear in particle physics. Their energy density can change as the field rolls down a potential landscape. This provides flexibility standard dark energy lacks. But there's a problem. Time-varying dark energy that resolves the Hubble tension conflicts with other observations. Models that raise the early expansion rate to match local measurements predict structure formation that doesn't match observations. Galaxies form too early or too late. Cluster abundances come out wrong. The cosmic microwave background third peak shifts. No simple time-varying dark energy model fixes everything. The void provides an alternative. Maybe dark energy is constant everywhere. Its effects simply manifest differently in different environments. In voids, less matter means gravity is weaker. Dark energy dominates more easily. Expansion accelerates faster. In clusters, more matter means gravity is stronger. Dark energy's effect is partially counteracted. Expansion accelerates more slowly. This creates apparent variation. Observers in different locations measure different effective dark energy strengths, not because dark energy changes, but because local conditions change how expansion responds. Think of wind speed. The atmosphere has a certain wind velocity at altitude, but ground-level measurements vary. Trees, buildings, and terrain modify local wind. Measuring wind from different locations gives different values. All are correct locally. None represents the global average. Similarly, measuring expansion from inside a void gives a void-specific rate. It doesn't represent cosmic average expansion. Dark energy's true strength is revealed by averaging over the entire universe. The cosmic microwave background does exactly this averaging. It samples the whole cosmos. Its prediction for dark energy strength is correct globally. Local measurements sample non-average regions. They yield modified values. This explanation preserves the cosmological constant model. No new physics required. Dark energy remains Einstein's simple vacuum energy. Its strength is truly constant everywhere. Observations only appear contradictory because different methods sample different environments. Does this mean dark energy research should focus on local variations? Partly. Understanding how dark energy interacts with large-scale structure matters. Its effects depend on matter distribution. Voids amplify its influence. Clusters suppress it. Mapping this variation tests models. But the fundamental question remains: what is dark energy? The cosmological constant explanation is elegant but unsatisfying. Why does vacuum energy have exactly the observed strength? Calculations predict it should be vastly larger. The discrepancy is 120 orders of magnitude. That's the worst prediction in physics history. Quintessence fields avoid this by being dynamical. Their strength adjusts naturally during cosmic evolution, but inventing new fields without independent evidence is speculative. Maybe dark energy is a hint of modified gravity. Perhaps Einstein's equations need correction at cosmic scales. Several proposals modify general relativity to produce accelerating expansion without dark energy. These models have varying success. Another possibility is that dark energy doesn't exist. What we interpret as accelerated expansion might be an artifact of living in a void. If voids expand faster than average space, and we're in a void, we'd measure faster expansion locally. We'd infer dark energy, even if none exists. This radical idea has been explored. Models without dark energy, but with significant void structure, can mimic dark energy observations. But they struggle to match all data simultaneously. The cosmic microwave background independently requires dark energy. So do galaxy cluster counts. Eliminating dark energy entirely doesn't work. The void affects how we measure dark energy's strength. It doesn't eliminate the need for dark energy. Future observations will clarify this. Measuring expansion beyond the void will test whether apparent dark energy strength varies with location. Mapping structure precisely will show how dark energy influences void growth. Comparing multiple independent methods will reveal whether contradictions persist after accounting for local effects. Dark energy remains cosmology's deepest mystery. The void hypothesis doesn't solve it. But it does show that interpreting dark energy observations requires care. Local measurements might not represent global properties. Understanding our cosmic environment is essential for understanding dark energy itself. The final lesson is humbling. We're not in a typical location. The universe around us doesn't represent the universe as a whole. Our measurements reflect local conditions more than global properties. This challenges a century of cosmological assumptions. Since Edwin Hubble discovered expansion, astronomers assumed measuring nearby space reveals universal properties. Distant galaxies recede. Their recession velocity increases with distance. This relationship, Hubble's law, describes cosmic expansion everywhere. Or so we thought. The KBC void shows this assumption is incomplete. Hubble's law applies, but the proportionality constant, the Hubble constant, varies by location. Inside voids, it's larger. In clusters, smaller. Averaged globally, one value. Measured locally, a different value. This doesn't break Hubble's law, it refines it. The relationship between distance and velocity still holds, but the expansion rate is location dependent. Why did we assume uniformity? Philosophical reasons, partly. The cosmological principle emerged from the Copernican principle. Earth isn't special. The solar system isn't special. The galaxy isn't special. Extending this logic, our cosmic neighborhood shouldn't be special either. Practical reasons, too. Cosmology is hard enough assuming uniformity. Inhomogeneous models require solving Einstein's equations in full generality. That's mathematically intractable. Homogeneous models simplify calculations enormously. If the universe is uniform, one set of equations describes everything. This assumption enabled modern cosmology's success. But assumptions must be tested. The KBC void is the test result. Uniformity holds approximately at some scales, average over 10 billion light-years, and variations smooth out. But at scales of billions of light-years, significant structure exists. The universe is lumpier than the cosmological principle suggests. This has consequences. First, measurements must specify what they're measuring. Local expansion rate differs from global average. Both are valid. Both are measurable. But they're different quantities. Conflating them creates confusion. Second, interpreting observations requires understanding location. We can't simply assume our data represents universal conditions. We must map our environment, account for local structure, correct for peculiarities. Third, the cosmological principle needs qualification. At small scales, the universe is obviously non-uniform. Planets, stars, galaxies, all are inhomogeneities. At intermediate scales, clusters and voids create structure. The principle only applies at large scales. How large? Apparently larger than previously thought. Maybe averaging over 10 billion light-years is necessary. Maybe 20 billion. The observable universe's diameter is 93 billion light-years. If uniformity requires averaging over 20 billion, significant variations exist within our observable region. We see only a small patch that happens to be underdense. Other patches might be overdense. True uniformity appears only beyond our observational horizon. Fourth, the rarity of our location must be addressed. If we're in a 1 in a billion void, why? Anthropic selection offers one answer. Observers exist only where conditions permit. Maybe voids provide favorable conditions. Lower galaxy density means fewer mergers, less radiation, more stable environments. Complex chemistry might thrive better in voids. If so, most observers would find themselves in voids despite voids being rare. This is speculative but not illogical. Alternatively, voids might not be as rare as lambda-cold dark matter suggests. Maybe the model underestimates structure formation. Maybe initial fluctuations were larger. Maybe dark matter behaves slightly differently. Adjustments could make large voids more common. Then finding ourselves in one becomes unsurprising. Fifth, this discovery emphasizes empiricism over dogma. We believed the universe was uniform because it seemed philosophically right. Observations now challenge that belief. Science progresses by updating beliefs when evidence demands. Clinging to the cosmological principle despite contrary evidence would be unscientific. Accepting large-scale inhomogeneity is uncomfortable but necessary. Finally, this reminds us of science's provisional nature. Today's certainties become tomorrow's approximations. Newton's gravity was exact until Einstein refined it. Einstein's cosmology assumed uniformity until observations revealed structure. Our current understanding will likewise be refined. Future discoveries will show where today's models fail. That's not pessimism, it's realism. Science never reaches final truth. It approaches truth asymptotically. Each generation sees farther, understands deeper, but never achieves complete knowledge. The KBC Void is this generation's challenge. It's evidence that our cosmic address matters, that local conditions affect observations, that the universe is richer and more complex than simple models suggest. Whether it resolves the Hubble tension completely remains to be seen. Whether it requires abandoning lambda cold dark matter or merely adjusting it is debated. Whether future observations confirm or refute it will unfold over the next decade. But one thing is certain: we're living inside a bubble, an enormous underdense region spanning 2 billion light-years. This affects everything we measure, everything we infer about the cosmos. Understanding our location is essential for understanding the universe. The journey continues, the data accumulates, the mystery deepens. And somewhere out there, beyond the void's edge, the universe expands at its average rate, oblivious to our special circumstances, indifferent to our measurements, waiting for us to figure it all out.